Today we're going to talk about rational functions and asymptotes. This is going to be a really big lesson, a really important one, so pay really close attention today. So a rational function is any function that can be written in the form of f of x equals n of x over d of x, which basically is numerator function over denominator function. So, for example, 1 over x is a rational function. Find the domain of f of x is 1 over x and discuss the behavior of f near any excluded x values. Okay, well, obviously a denominator can never be 0. So if I plug 0 into this thing, this is undefined. So I'm going to go ahead and put a little infinity sign in there. If I plug in -1, I get 1 over -1 is -1. If I put in +1, I get 1 over 1. If I put in 0.5, 1 divided by 0.5 is 2. 1 divided by -0.5 is -2. 1 divided by 0.25 is 4. This would be -4. 1 divided by 1/100th is 100. This would be -100. So what you can see happening here is as you're getting closer and closer to 0, on this side, it's getting bigger and bigger and bigger. On this side, it's getting smaller and smaller and smaller. That creates something called an asymptote, which we're going to talk about quite a bit. Okay, so the line x equals a is a vertical asymptote of the graph of f when f of x goes to infinity or f of x goes to -infinity as x goes to a, either from the right or the left. Okay, what does that mean? It means this, just like when we had this last function, f of x was 1 over x. Okay, so we looked at the graph, it went like this. As you got closer and closer to 0 from that side, it went to -infinity, and as you went closer and closer to 0 from that side, it went to +infinity. And so what you get is you get this imaginary line right here. It's a vertical line. It's called a vertical asymptote. It's discontinuous there because you can't draw this without picking up your pencil. Okay, you can draw this side, you can draw this side, but you can't draw it all connected. It's just at 0. Now, be really careful when you're using a graphing calculator, depending on how new it is. A lot of times what it'll do is it will look like, it will do this. It will look like it's connected, but it's not. It's just a graphing error on some of the older graphing calculators. You just got to recognize that there's a vertical asymptote right there. So the line y equals b is a horizontal asymptote of the graph of f if when f of x goes to b, or when f of x goes to b as x goes to infinity or -infinity. So on this one here, we have a horizontal asymptote right here. Because as the bigger this number gets, this goes to 0. And as the smaller this number gets, this goes to 0. But you can never get 0. You can't take 1 and divide it by anything and get 0. It's impossible. Okay, so here we got a function, f of x is 1 over x minus 2 plus 3. So we've got the curve here and here. We've got a vertical asymptote at 2. That's when the denominator is equal to 0, when x is 2. And then we've got a horizontal asymptote at 3, because as this shrinks to 0, then this becomes 0 plus 3. And so you have a horizontal asymptote there. So you can see here's my horizontal asymptote and my vertical asymptote. Let f be a rational function, n of x over d of x, where n of x and d of x have no common factors. The graph of f has vertical asymptotes at the zeros of the denominators. So anytime the denominator is 0, you got a vertical asymptote. You can have as many vertical asymptotes as there are. I mean, you can have tons of them. if the degree of n of x is less than, so the degree of the numerator is less than the degree of the denominator, then there is always a horizontal asymptote at 0. For example, and you want to know this, okay? You're going to use these three statements here all the way through calculus. Okay, so if you have a function and the degree of the numerator, let's say it's x squared in the numerator, and it's smaller than the degree of the denominator. So let's say this is x to the 4th. So degree 2, degree 4. As x goes to infinity, this is going to get big, but this is going to get bigger way faster. And so you get a fraction where the top is shrinking in comparison to the bottom. That means that that's getting to be a smaller and smaller number. It's going to shrink to 0. If the degree of the numerator is equal to the degree of the denominator, then there is a horizontal asymptote at the quotient of the coefficients of the leading terms. Okay, what does that mean? That means something like this. I've got f of x is 2x squared plus 1, and I've got over 3x squared minus 6x plus 2. Okay, the degree of the numerator is 2, the degree of the denominator is 2. That means that there is a horizontal asymptote, and it's at the quotient of the two leading coefficients. So all I got to do is take 2 and divide it by 3. There's one at 2/3. Right? So find all the asymptotes of the graph of these rational functions. So the first thing I'm going to look at has a denominator. When's the denominator going to equal 0? And this is never going to equal 0 because I can never put any number in here. I would need something to make this -1. And you can't square something and make it negative. So this has no vertical asymptote. Okay, it does have a horizontal asymptote. It has a horizontal asymptote at y equals 0. Now, why is it y equals 0? I'm degree 1 on the top, I'm degree 2 on the bottom. That means this is going to grow much faster than this is, and therefore this is going to shrink to 0. Okay, over here, I can factor the bottom of this. This becomes x minus 1, x plus 1. Okay, that tells me that x can be 1 or x can be -1. That's going to make the denominator 0. So this has two vertical asymptotes. It has vertical asymptotes at x equals 1 and x equals -1. It also has a horizontal asymptote. Because the degree of the numerator is 2, and the degree of the denominator is also 2. So I take the leading coefficients, 2 and 1, I divide them. 2 divided by 1 is 2. It has a horizontal asymptote at y equals 2. And I'm done with that one. Now, you can have as many vertical asymptotes as there are. In this case, there was 2. In this case, there was 0. You can have at most 2 horizontal asymptotes. There's also other asymptotes. They're diagonal. So you have a graph like this. You can have an asymptote that kind of goes like this. That's called an oblique asymptote. If you have a horizontal one, you cannot have an oblique one. And we'll talk about when you get an oblique one later. Find all the asymptotes and holes in the graph. Okay, so the first thing you want to do, you know this thing's going to have a horizontal asymptote because the degree is 2 and the degree is 2. All right, but what you want to do is you want to factor these things. So factors of x squared are x and x. Factors of 2 are 2 and 1. I need a plus 2 and a minus 1. Down here, I get an x and an x. All right, I got 2 choices. I can use 6 and, no, 2 and 3. 2 and 3. Think of something else. Okay, it's going to be -3 and plus 2. All right, so here's the thing. Check this out. I got an x plus 2 and an x plus 2. Those cancel. This function looks exactly like the function x minus 1 over x minus 3, except for one thing. It has a hole at negative 2. Anytime your factors cancel out, you're going to have a hole. Okay? So this thing has a hole at x equals negative 2. Now, you get fooled on a graph on your graphing calculator because your graphing calculator literally eliminates 1 pixel. So if you're not even zoomed in, you might not even see it. Okay? That's why I always want to factor this thing and check this way. Anything that cancels out, you've got an asymptote. Okay. Now, this has a vertical asymptote. Or I'm sorry. I think I said that wrong. Anything that cancels out, you got a hole. Now, this has a vertical asymptote at x equals 3. It's going to have a horizontal asymptote at 1 divided by 1, so the y is going to be 1. So you got one hole, one vertical asymptote, one horizontal asymptote. For the function f, find the domain of f, find the vertical asymptote of f, if there is any, find the horizontal asymptote of f, if there is any. Okay. So, to find the domain, you got to consider what numbers can you put in. Now, usually what I consider is, can I put negative numbers in here? Yes, I can take negative numbers and cube them and square them. That shouldn't be a problem. I can do that with positive numbers. I can do it with 0. So I don't have any problems here, except, is the denominator ever going to be 0? So I'm going to take that denominator, negative 2x cubed plus 16, set that equal to 0. Move this over here, so 2x cubed equals 16. X cubed would equal 8 when I divided both sides by 2, and then I would cube root that, and I would get x is 2. Okay, so this thing is 0 if x is 2. That's a problem. 2 is not in the domain. So for A, I'm going to write the domain is all real numbers except x cannot equal 2. That's what that means. The domain is all real numbers except x cannot equal 2. It can be anything else. Okay, B. Does it have a vertical asymptote? Yeah, it has a vertical asymptote when the denominator is 0, and the denominator is 0 at 2. So this has a vertical asymptote at x equals 2. Does it have a horizontal asymptote? Well, the top is degree 3, the bottom is degree 3. So I can ignore all this stuff over here, and it's going to be the quotient of those two, so it has a horizontal asymptote at y equals negative 3/2. Now we're going to talk about why we do this stuff a little later, because when we start analyzing graphs, we're going to want to use all this information. And basically what I can do is I can take a really complicated graph like this, and by analyzing it properly, I can graph this thing by hand very accurately by maybe graphing 1 point. Okay? So it's kind of like math magic. It's cool. All right, a utility company burns coal to generate electricity. The cost C in dollars of removing P% of a smokestack pollutant is given by C equals 80,000 P divided by 100 minus P. For 0 is less than or equal to P is less than 100. Obviously, it can't be 100 because that would make that 0 and that would make that infinity. Graph the function. Are you a member? Okay, so then you're a member of the state legislature that's considering a law that would require utility companies to remove 90% of the pollutants from their smokestack. The current law requires 85% removal. How much additional cost would the utility company incur as a result of the new law? Okay, so let's get out our handy-dandy TI-84 plus C Silver Edition graphing calculator. And let's go into y equals and clear out any equations that are in there. And let's put in 80,000 x divided by, in parentheses, 100 minus x, close the parentheses, and hit enter. And then our x can go from 0 to 100. So let's go to our window and change our x min to 0 and our x max to 100. And our x scale will go by tens because 1 is going to be too tiny for that. Let's make our y min 0 because our cost could be 0. And I don't know how big this is going to get. I think it gets pretty big. Let's put 100,000 in there for y max, and we'll count by 10,000s. And then we'll hit graph. Okay, so you can see that your graph goes like this. Goes off the graph here. Okay, and we had, this was 100,000. And this was 100 way over here. Okay, so this goes up into the millions. So now I can use my table. So if you look where the graph key is over here on the far right above it says table. And right above window it says table set. So do this, go to second window, and it says table start, put an 85 right there. And then the little triangle table means change in table. We'll just leave that 1. And then go to table. And what it'll do is it'll start you at 85. And it says it's going to cost $453,333 to get 85% of the emissions out of there. Okay, now, what's happening is it's growing so fast. If you look at 90%, that's 720,000 to get that additional 5%. Now, if you kind of scroll up, if you went the other way, 5%, if you went to 80, 320,000. So that changed by 233,000. No, 133,000. But this 5% cost you almost 300,000 more. So this is getting incredibly expensive. So the question is, do you vote to do that? Now, here's what you got to take into consideration. This company is not going to eat that. They're going to pass that on to their customers. Okay? So their electric bills are going through the roof. Okay? So you got to balance what is, does that 5% really get you much? Or is it, can we live with the 5% versus the cost, the additional cost? Okay. So that brings us to the end of our lesson here. This is our last lesson for chapter 7. Here's your assignment. And again, I forgot to put the assignments on the end, so I will go ahead and do that today. And I will also post those in Google Classroom because it's a much better picture. So have a good weekend. Talk to you later.